Hello everybody. It is a very compact slide, so I hope it will be good. So I will talk about runtime application security protection, reverse and bypass. Who know such kind of tool, such as Dashboard, Verimatrix, and so. Okay. So before, my name is George, and I was a security evaluator on payment application, reversal developer, and so. And I am mainly known as the author of Excalibur, and Antiworking is the last tool. It is a library for FRIDA, which allows you to hook SVC call easier and use the same API than Interceptor's API, but with the SVC. Okay, so I will start by explain you what is the context, and next we will move into inside how such kind of protection work. It will be mainly focused on anti-hooking and some kind of obfuscation specific to such tools. And finally, we'll talk about how improve your FRIDA hook in order to hook some context which are difficult to reach, such as follow thread, follow fork, and so on. Why this talk? First is Android Protection Tools Editor, not consider reverse engineering and public bypass as vulnerabilities, and not offer bug bounty or rewards. Next is the assessment of this kind of protection is mandatory for most of security certification, such as banking and banking certification, EMVQ certification, and so. And finally, we try to contact them, but they not respond, and so on. Before to continue, just let me know all you will see has been done inside during security assessment, and not in the web. Okay, so SPT stands for Software Protection Tools. It is the name from EMVCO, and runtime application security protection is a kind of protection provided by SPT tools. And for the rest of the talk, SVC stands for Supervisor Core, which is interrupts to perform syscall on ARM64. Okay. So what is a software protection tool? Such tool contains at least 3 layers of protection. The first targets only that resources from the APK. That means some YAML and properties files, and or JS or HTML if your application uses PhoneGap or such kind of framework. For this kind of resources, as resources are flat files, they are mainly protected by integrity checks. Not only checks provided by Android API, but also custom integrity checks done with a random file and custom CRC 32 checksum at runtime. Lot of SPT also perform encryption of such resources and decipher it at runtime. The next layer is protection of code. Here, when we talk about code protection, it is mainly about anti-tampering. That means if you hook a method, the anti-tampering should prevent the application to continue on the good path if you change the path with this hook. Anti-hook is mainly mechanism to detect threader hook, for example, or expose hook into memory or using some checks on file system. And finally, code obfuscation and code decryption are common. The next layer is protection of the app overall. Of the overall app against emulator or rooted devices, such as devices with Magisk, network protection by implementing SSL pinning in order to prevent HTTPS man in the middle. And finally, the application and the countermeasure offered by the SPT are protected by anti-hook and code obfuscation provided by SPT editors. In an SPT, there is a lot of security functions. Some are listed here, but we only covered some. Okay. So, now I will talk about how we sampled some target application and the RESP. So we select industrial grade and certified RESP, such as you can find on EMVQ certified protection tools. And for each, we reversed some of native library packed with protected application in order to identify and write Yara rules for each. And you deploy such rules on Kudos in order to automate the sampling of APK. We can protected APK. So here you can see a kind of Yara rules we used to target specifically a single version of a single SPT. The first part, this rule is not based on string, so it is harder for the SPT editors to bypass it or correct it. So the first part here is a XOR, a simple XOR and hash comparison extracted from the anti-hook functions. The second part is are two patterns from string decryptions, and the last is a common patterns because SPT tools provide functionalities as a native library, and this native library avoid to use the libc, so most of system calls are inline, but the system calls are often wrapped into another function. So we can identify an SPT by the count of wrapped SVC. In this case, the editor of this SPT tool always provide a library with 6 or 8 SVC, wrapped SVC. So with this kind of rules, we are able to gather more than 300 IP keys. Okay. So next, I will talk about what is a runtime application security protection. The first part, the first step is the entry point as any application. As a runtime application, so such as kind of tool is native, is provided as a native library. The entry point is often the init array of the Elf file or the JNE on road. From this point, it starts by performing hook detection. This hook detection starts by, for example, by checking on proc self maps in order to detect Frida agent or other libraries, and it creates a new thread, and this thread will check if the main thread is also hooked. And it is interesting because it is harder to hook a shield thread than the main thread by default. Next, on the hook detection is right. It's load the anti-debugger detection. Anti-debugger is a bit different because it performs also a fork at start in order to pairwise the parent with the fork in order to prevent GDB to be attached to the parent. I will explain it later. And each thread performs own debugger detection, such as ftrace detection by checking the content of proc safe status files or more. And another, once this kind of check are done, the thread, the child thread from the hook detection perform again a hook detection check on all thread available. Yeah, and it continue. Anti-debugger pop a new thread, and this thread perform ptrace attach or PRCTL in order to prevent GDB to perform core dump. And now the SPT will deploy environment detection, which is emulator detection, root detection, integrity checks, and more. Each time a protection layer is deployed, or each time a new thread is created, all detection already available are rejected. Okay. And finally, the execution flow return into the app, and you have a lot of thread running in background and and doing such kind of checks periodically or only on demand when the application want to do something sensitive. Okay. So now I will explain you how obfuscation of these tools is very different from common obfuscation, and how anti-hook is implemented. Okay, before to continue, I will introduce the latest tools I developed, which is Interrupter. Interrupter is like strace, but it is done exclusively from Frida using the stalker. It provides a pretty hook coverage generation. It generates a drcov file you can import into IDA or Kidra. And it provides also pretty print where every constant in a C-score are parsed, and it is very useful. So now I will talk about this step inside the WASP workflow. I think the main obfuscation improvement has been against about string comparison. Because traditionally, most of protection tools search file based on a string or compare existing file with a string or package name with a string, such as root beer or even anti-footer from Da Vinci sec. So it is very easy for an attacker to gather the list of detection patterns and make a hook which tamper the value in order to hide such detection patterns. Here you can find an example from one of certified products which not used hash-based comparison but classic strings. At the left you can see string deciphering is inline. So you cannot hook a function in order to retrieve such strings at runtime, but it is very easy to script and perform P-code emulation inside Ghidra in order to retrieve such strings. That is you can see at the right. For information, every script will be available on the GitHub of this talk after the talk. Okay, so some editors create another concept. They change of paradigm and replace, and they tried to replace search or compare with string by enumerate folders, for example, hash file name of every entries and compare each to already hashed value hard-coded in the application. For editors, I think this improvement prevent an attacker to retrieve all patterns, because I think attackers have a specific context of execution. So maybe the attacker will not trigger anti-emulator if he used physical devices, for example. So the attacker cannot be able to retrieve all blacklisted patterns. Another thing is more easier to implement or inline such kind of operation. And finally, it is less easy to hook for us, and it not used Android API. Okay. So the pseudocode at right is extracted from the parsing of proc self maps, while one of protection tools perform anti-hooking. The aim of this code was to identify if the path of the file mapped at a region come from a blacklisted or whitelisted here folder. So instead of comparing the begin of each file path with a hard-coded system /lib strings, for example, it hashed this value and compared this value with hard-coded hashes. For the reverser, it is the code is very slow to understand. Here you can see how it is different from code point of view and for the attacker, which would hook the function performing the hash. In the first part, it is obvious. You can hook any function from libc using string arguments such as fopen, and you will be able to understand the workflow of the application change when this when the particular strings appears in the hook logs. But in the case at left, it is more difficult to follow what happens. Hash, for example, in this case, it's inline, and it starts by doing some SVC in order to browse the content of system/etc. The aim of this function is to find the entries containing system/etc/public libraries, I think. Okay. So for each entries, the tool will hash each byte one after byte one by one. So it is difficult to hook only a function in order to retrieve the value which has been hashed. And another thing, it is this kind of function perform, in fact, start with of the string instead of hash of the entire strings. So okay, at the right you have the code corresponding to the hash function in this case. And finally, for this case, you can implement a hook with an interrupter and interceptor. Okay. So this hook will deploy interceptors on the function doing a hash of each byte when the dynamic linker will load your target library. And the hook of the hash, as the hash function has two arguments. One of the arguments is the first is the byte which is hashed, and the second is the index of this byte. By implementing the state machine inside the hook, we are able to retrieve entire strings which are hashed, and we can show at the right the workflow change when the hash value is correspond to the string public.libraries. Because after it open and read the content of this file. Okay. Before to come back to public libraries during Antiworking, I will continue with obfuscation. So maybe you already encounter this kind of case where you have data inserted between part of code inside your binary. It is a common trick to hide the stack and replace the stack by it will use a link register as a stack pointer. Sorry. Okay. So first, it starts by following the orange path, and it jump to the label which ends by 9.4. Do you see the red pointer? Okay. So it's in this case the execution follow the orange path and jump to this one. And when here it is a branch with link register, that means when it jump back, x30, which is the link register, is set to PC plus 4, so it points to this section, and the execution continue and jump by following the green path, and in this section the stack, instead of using a stack and stack pointer and data located, hard-coded data located into other section, it read data stored at the location pointed by link register. By doing that, Ghidorah is not able to retrieve the initial value of local variable, and sometimes local variable cannot be entirely not discovered by Ghidorah. Additionally, it is not considered at a call, so there is no cross-references and so on. Now, I will talk about another kind of obfuscation, about DEX classes. I think it is not really an obfuscation, but a way to do something earlier than common entry point of Java of Android application. So for most of developers, the application entry point is the application attached base context method, which is implemented by the classes where the full class name is inside the application entity into my Android manifest. But in fact, you can override the app component factory, which is the classes inside Android which perform instantiation of any components declared inside Android manifest. So this app component factory perform initialization of providers, activities, services, and so, and also it defines the default class header of the application. And it is the case here. Here, it will replace the past class header which search classes inside the AP key by an in-memory DEX class header which with a buffer deciphered and rebuilt at the application starting. In this application, into the initial application, there is only 3 or 5 classes with the Packer code, and other classes, just less than 1,000 classes, contains on each one only a byte array of 2,000 bytes. And at runtime, during when instantiate class header is called by the app component factory, every byte for every byte array from every classes are concatenate and XORed, and it results as a zip which is uncompressed and defined as a new dex file into the in-memory dex class loader. So it replaces the default class loader of the application by your unciphered dex buffer. In this kind of packing, it is the best way is to perform it statically by implementing a script which parse small file and concatenate byte array and perform operation. And the result at write is not obfuscated. It contains all dexes the application. Okay. Just another trick used by this kind of tools is to diversify how the application check if a file exists or not. The application could use fopen, for example, but by using passconf, it allows the protection tools to hide the return value. It is less obvious to read when a file exists or not, because by doing a passconf, the file exists only if the return value is 0x1000. So it is just a small trick. But at a syscall level, passconf don't do an OpenNAT system call, but a stat EFS. Okay. And the last, but maybe the order to explain. The packed self-modifying code is a kind of matryoshka from native. Okay, so remember previous explanation about how break stack analysis. It is the same tricks, but here you have to okay. You see the pointer? Okay. So now when the execution follow this part of code, the link register point to relative offset and size, both value. Relative offset is a location inside read-only data section, and the size is a size of a subset of this section. When the execution continue, it will change protection of the range where arrow data is mapped and make it read-write executable, and perform a malloc, deciphered the application patch or deciphered the code located into arrow data and remap it into another location. And the execution jump to this new location, and this freshly mapped region contains also another section of ciphered data, which is deciphered by this one, and it mapped several memory regions. Here you can show the output of interrupters, and you can show there is lot of memory map. The first one point to this region, and the other point to freshly create region. Unfortunately, at this step, it is just an allocation, so we have no data to dump by hooking such system. Here we see there is an open hat which happen when all previous mmap are done, and this openNet is an open of proc self-status, which is commonly used to detect if F-stress debugger is loaded. So for us it is interesting because we could hook openNet syscall and dump all previously allocated region content. So, at the code, it's like this. With interrupter, we trace the main thread. And if we hook the instruction, so we hook SVC call before to jump to the next instruction, and we show if the resulting addresses. Okay. So the X1 contains the protection flags which has been used when the execution flow enter into mmap. So this hook will push into an array the address and the size of the mmap call only when the protection flag is read write execute, and it is one of both size. This size come from this call, all allocated region as a size of 0x1, 000. So it helps us to filter what we will dump. And next, we use our openNet of proc self-status, and we'll use a file API from Fluida in order to dump each region. And in our case, such region is not useless. In fact, each region is the region where the start routine of shield thread are located. So the execution will jump to another section, such as part X, and this one will create new thread, and each thread will start its execution by executing this corresponding part. So in order to change the execution here, we should hook pset create in order to redefine where the start routine is located, in order to be able to execute code prior to the rest of the execution. If you are interested, we could talk about that later. Okay. Now I will talk about anti-hooking. So remember, anti-hooking is next after the entry point. Here you can see a common roadmap for anti-hooking. It starts by reading prop maps contents in order to search suspicious libraries, and it will continue by checking all range or and symbols. So in some case, we can see. Oh, sorry, just see the time. Just see the time. In this case, the execution starts into the protection libraries, but the protection remap itself at another location and jump to this new location at the same offset than the current execution. So it is a kind. I think it is a kind for editors to protect against some hooking, because you need to know the new absolute offset of the hooking function, and this offset is relative to the location where the new where the application libraries has been remapped. Okay. So now we'll see how the protection tools detect how Frida gadget, how Frida agent or unexpected code is existing to the application. Imagine we have a group of the content of the prop maps is content every memory region involved into the application, but it will start by filter only region with execution attributes. This region is mainly all executable region should be only should contains only executable region mapped to file should okay. Every executable region which are mapped to files from file system should je refais. Do it again. All executable files involved into application are mapped in memory, and these files should be each file name should be listed into one of these four sections of these four group. For example, if it's if the library come from Android image, the file name of this library should be contained into this file, and it is always true for vendor libraries, manufacturers, and libraries packaged with application. So, if a file mapped in memory are not defined into one of these files, it is unexpected executable file and suspicious. So at the right, we have the a log from the prop maps, and when the application enumerates reads the content of prop maps, for example, it could read the file line by line and check if if the path of each file is is defined into vendor, or in this case, I think it is font file, maybe. And here, the library, sorry, the file are libview, Chromium, which are whitelisted in the system etc public library. But here we have free agent, and this file and any library loaded by using LD preload are not contained into any of this whitelisted file. That is why the protection tools detect a suspicious file is loaded in memory. But it's not sufficient, because now the tool must detect where each symbol are located in order to detect if a function has been hooked or not. So when the protection tools parse the entry of each line of prop maps, it parses region, start address and address, and also it has also the attributes in order to detect execute only region and if a region is executable or not. Next, it will use this trick with DL open in order to detect if the library is already loaded or not into the process. And the final structure we try this one. And next step, once the entire contents of proxaf maps has been parsed, the hook detection mechanism will browse this chain list of regions of regions, and it will check if at the begin of each region there is a F magic. So if it's the case, it will take the path of the file associated to this region, and it will load it as the linker could do it. But instead of using the linker, the protection tools will parse the header of the elf, and it will try to resolve itself all symbols, and it will perform some comparison on what is the address of symbols in the current mapped region, and what address it could be if the file will be loaded again. Theoretically, address should mismatch if you hooked the function. It is used, for example, in this case, if you use java.perform in your Frida hooks, it will change libart. It will remap some region from libart, and it will trigger this detection. And in fact, this kind of detection can provide anti-hooking against exposed and more. Okay, at the right, you have a libc, the mapping for libc of inside a clean process, and at the right for the looked process. So at this step, we could we have two ways to bypass the anti-hook. The first is specific to how the hook work, as I explained. you could patch the linked list. The linked list in order to stop the analysis, or we could lift the output of the read of proc self maps in order to hide FRIDA. So this one works fine, but it is too much specific to the protection tools. So we prefer. I think it is better to lift proc self maps contents when SVC read is done. But application not used line by line read. Most of application read byte one by one, so it is harder to hook. Or sometimes the application perform a read with a random length. So if you to lift the proc self maps, you need to know the path of the file which is mapped, but also the protection and also the region in order to compare it to a clean process. So we must be aware of a full line. So if there is a random length, you need to implement a smarter hook. It's not interesting, but I provide some hook scripts to perform that inside the slides. But I have not enough time, so I continue. It is just an example how to patch the output buffer of the read syscall using FRIDA. It uses the memory API scan sync in order to search, for example, RWX patterns and replace it by in this case just read -x. Be aware when you do that. If you use write byte array, you should keep the same length. Okay, another kind of FRIDA detection is to search injector of FRIDA and use DLC, for example, and or to search for threads. Because FRIDA has 2 threads with a specific name. So if you use the stronger FRIDA, for example, the server patch such strings, but if you use official FRIDA binary, you could be interested by the tampering of such values. So in this case, I think there is a three way to do that. First is a read as in previous case, or if mmap is used to dump the content of proc self task statue, you could change the file descriptor in order to point to another clean thread statue file. And so, and it is the hook to perform what I explained. And I have not the time, but I think the most important is to keep all hook consistent, because protection tools implement a lot of way to detect what you do. So if you hook only one way, and it will detect an issue by comparing the results of every function, every detection mechanism. I give you an example of F-threat detection is done at native level. by reading the content of proc self statue files, for example, and it research if trusser PID is up to 0, and it will do the same from Java, but it will use the string contents, and it will compare the results. So if you hooked C-score or a libc function in order to tamper the result, but not the Java detection, the protection tools will detect you try to tamper the result. There is a lot of other kind of detection you can find into the site. And another interesting example is how the application prevent GDB or debugger to perform a core dump. It is done by doing a PRCTL with this constant set dumpable. When you hook such kind of code of syscall, you should be aware. You should find a value which caused the less side effects on the application. And here it is the hook to change the PRCTL. And next is how the anti-debugger work into the Rasp with a fork and so. So this part of code performs the fork. That means this part will be executed only by the parent, and this part will be executed by the shield process. And in this case, the shield process, we start by doing a kind of attach. After the fork, the shield process will do a ptrace attach on the parent. So it is how it prevents GDB, for example, to be attached to the parent. And here I provide a hook which replaces the attach by a detach, because detach is a constant which has the less side effect on the application. Okay. And finally, in order to automate all, we have another problem. First, the idea is to use only agent side script in order to keep the application repackageable with a Frida gadget, and you will make a universal script targeting a lot of protection tools and more. So remember, you would like bypass all, but there is a lot of thread, there is fork, there is hook into entry point of libraries, there is hook inside app component factory prior to application attached bus context, and it all are possible with Frida, but it not work out of the box. So you should implement all. You should implement hook which allow to hook some point where you could be able to deploy your final hook. So, for example, to perform a hook of if you, in our case, instead of hooking from application attached bus context, as lot of protected application perform a system load library of the SPT libraries inside app component factories. You should hook. You should perform a Java hook using Java de-optimize everything inside Threader or Java perform now. But if you use Java use inside this context, you should be aware some class will not be able because you are very at the beginning of the application. So at this step, only classes from Java package or Dalvik package are available. And you should also hook. You should deploy hook on method which are defined dynamically only when the classes implementing these methods are available. So that means you should hook class loader or dynamic loading of class loader. So I provide you. Sorry, I have not enough time. The first point, the GNI unload, is a classic location where the Java perform. If you put an interceptor attached into a Java perform, it will be triggered at the beginning of a GNI unload. But sometimes you should be interested to deploy some hook before the entry point, as you could do by using leaf with a Threader gadget in order to link it statically or dynamically. Sorry. Okay, sorry, I can't finish. Other challenges are multi-threading, because when you do Java perform or interceptor, it will patch region which are shared by all thread. But if the application is inline and use a lot of syscall, you will be you must use stalker, but the stalker not is per thread. So you should implement follow thread. And you can find it. Sorry. Okay.
Yeah, awesome. Would you like to?
I think I
minutes for questions, maybe.
Yeah.
Are there any questions for Georges? Yeah.
Thank you for the talk. How often do you find those kind of how often do you find this kind of protection in apps? It looks like it's very strong protection.
It is very common inside payment application, Oscar emulation. That is application performing payment on terminal with the phone, and also on mobile point of sale. That is a terminal a payment terminal inside the phone. When the customer put his credit card on the top of the phone of the vendor, and some sensitive apps which require certification by state, and maybe a game.
But a lot of those those protections are very time consuming, no? Like the matryoshka. Matryoshka.
When you hook it, yes, it is slow. But I don't talk about it, but a lot of protection tools perform time measurement in order to detect if you try to hook or tamper it. And sometimes time measurement is done by several threads, so it can be very difficult to spoof the behavior. But Matryoshka, for example, is only done at the beginning, at starting the application. So it is not so important for banking industry.
Thank you. Any more questions?
Yeah. Just a quick one. I have seen protection against pit race, but I have not, or at least that I'm aware of, listened anything about symbol interposition with LD preload, for example. Are there any countermeasures that you have taken for this?
Sorry, I'm not sure to understand.
So you said that you were putting some countermeasures against pit race, but did you also take into account symbol interposition with LD preload? Did you protect it against that?
Yes, I talk about LD preload during Antiworking because if you used LD preload in order to load a library which are not known by the platform as a built-in libraries, and if this library is not packaged with a target application, the anti-hook will detect this library is not expected at runtime.
Thanks.
Any last questions? Thank you very much for your talk, George. Please give him a big round of applause. Thank you.
Merci.